The next topic in our discussion of random variables and their distributions is expectation. Now, expectation is the process by which we obtain characteristics of distributions that are used in statistical applications. Let x be a random variable with sample space script a and PDF or PMF lowercase f. If x is a continuous random variable, then f represents its PDF, and if x is a discrete random variable, then f represents its PMF. Let g of x be a function of x. The expected value of g of x is denoted in the following way: capital E for expectation, and then the random variable or the function of the random variable whose expectation is desired. And we define it in the following way. Now let me just say that the concept, the idea of expectation is the same regardless of whether we're talking about a continuous random variable or a discrete random variable. Expectation is an averaging process. And really what we're doing when we calculate an expectation is we are calculating a weighted average. The method by which we calculate that expectation depends on whether we're dealing with a continuous random variable or a discrete random variable. If x is a continuous random variable, then its expectation of g of x, the expected value of g of x, is obtained by integration. On the other hand, if we are dealing with a discrete random variable, then the expectation of a function involving x is obtained via summation. Now, in each case, the terms that we are integrating or summing are the same. It's the product of the function whose expectation we're after, g of x, times the values of the PDF or PMF, depending upon whether x is continuous or discrete. So in each case, the terms that we are integrating or summing are the sum of the product of g of x and the PDF or PMF f of x. Now let's look at a few useful properties of expectation. The first is the expectation of a constant. So suppose that x is a continuous random variable with PDF lowercase f. Let g of x be a constant function of x. So, for example, let's let g of x be equal to b. Then the expected value of g of x, the expected value of b, by definition, is equal to the integral over the real line of the product of g of x and f of x. So we have the product of b and f of x as the integrand here. Using properties of integration, you'll remember we can pull that constant b outside of the integral, and so we have b times the integral over the real line of f of x. Now remember that one of the defining characteristics of a PDF was that if you integrate that function over the real line, you get 1. And so the integral from minus infinity up to infinity of f of x is just 1. And so what we have here is that the expected value of the constant b is just that same constant b. Now this result holds regardless of whether we're dealing with a continuous random variable or a discrete random variable. If x had been discrete, we would replace the integral sign by summation, and the exact same result would obtain. Now, the next property that we'll look at is the linearity property of expectation. So again, let's suppose that x is a continuous random variable with PDF lowercase f. In this case, we'll let g of x be a linear function of x. So for example, we'll let g of x be a times x plus b. Now you recognize this as the equation of a line. Here b is the y-intercept and a is the slope. Then the expected value, or the expectation, of this linear function of x, the expectation of a times x plus b, by definition, is the integral over the real line of the function g and f of x. So ax plus b times f of x. I can distribute the f of x, the PDF, across both terms in that sum, and then after doing a few steps of simplification using properties of integrals, this turns out to be equal to a times the integral over the real line of x times f of x plus the integral over the real line of b times f of x. Now you'll recognize this last integral as the expectation of b, which we just calculated, and you know that evaluates to b. In the first expression here, the first integral, we have the integral over the real line of x times f of x. And that is, if you go back and look at how we denote things, that's actually just the expected value of x. And so the expected value of this linear function of x, ax plus b, is that same linear function applied not to x, but to the expected value of x. And so we can state this in the following way. The expected value of a linear function of x is given by that same linear function or transformation, but of the expected value of x. And for this reason, expectation is said to be a linear operator or a linear operation. Again, this property holds regardless of whether the random variable x is continuous or discrete. So these two properties are very helpful. The expected value of a constant is just that same constant, and the expected value of a linear transformation of a random variable is that same linear transformation, but applied to the expected value of the random variable. Now, this can be generalized to linear functions of two or more random variables in the obvious way, and we'll actually do that in the not too far distant future in the notes. Now, let's look at some special expectations, the first of which is the mean of the distribution of the random variable x. Now, that is obtained by computing the expectation of g of x equal to x. And so in this case, the function g is just the identity function. Now, we denote the mean of the distribution by the mean of the distribution of x by this notation here, which we saw on the previous slide actually, the expected value of x, and also using this notation here, lowercase mu, and if we need to make sure that we understand which random variable we're talking about, we can put that random variable label in the subscript. Now, you've seen lowercase mu used to denote means of distributions and means of populations in previous courses. All right, and so we have two ways of denoting the mean of the distribution of the random variable x, using this lowercase Greek letter mu, which we would read this as the mean of the distribution of x, or this notation here, which we would typically read that as the expected value of x. Now, again, the concept of expectation is the same regardless of whether we are talking about a continuous random variable or a discrete random variable. The expectation process is an averaging process, and in particular, we're calculating a weighted average. Now, the weights that we're applying are the values of the PDF, if x is a continuous random variable, and the values of the PMF, if x is discrete. But overall, the concept is the same regardless of whether we're dealing with a continuous random variable or a discrete random variable. Again, the method by which we calculate it depends on whether we're dealing with a discrete or continuous random variable. If we're dealing with a continuous random variable, then we get the expectation via integration. And if we're dealing with a discrete random variable, we get the expectation via summation. So these expressions here are just special values of the more general representations where we're talking about the expected value of some function g of x of the random variable. All right. Again, with this, because this is the identity function or the identity mapping. Now, the interpretation of the mean of the distribution is that it's the center of mass of the distribution. So if you think about if we're dealing with a continuous random variable, for example, the continuous random variable has a PDF. And if you think about a graph of that PDF, drawn, with the, you've got a horizontal axis and then you've got the PDF above that. If you think about placing a fulcrum underneath that horizontal axis and then sliding the fulcrum and allowing that graph, that horizontal axis to rotate, so it's kind of like a teeter-totter, then the point at which that graph would balance is the center of mass of that distribution, and that is the location of the mean of the distribution. Or equivalently, it's the location of the expected value of the random variable x. Another special expectation, which gives us a useful characteristic of the distribution, is the variance of the distribution of the random variable x. Now, this is obtained by computing the expectation of this particular function of x, the square of the difference between the random variable and its expected value, or equivalently, the expected value of the square of the difference between the random variable x and its mean. Okay? Now, we've got, again, we have a couple ways of denoting this. We can denote it this way. We would read this the variance of x. We can also use this notation, which again you've seen in previous statistics courses. Lowercase Greek letter sigma squared. All right? And so the definition for the variance, expressed in terms of expectation, is that it's the expected value, or the average. Remember, expectation is an averaging process. So the variance is the expected value of the square of the difference between the random variable and its mean. If x is a continuous random variable, then we obtain that expectation via integration. And if we're dealing with a discrete random variable, then we obtain that expectation via summation. But in each case, the terms that we are integrating or summing are the exact same. We have the product of the difference between the random variable and its mean times the value of the PDF if we're dealing with continuous random variable, or PMF if x is discrete. So the terms are identical notationally, obviously, and the only difference is whether we're integrating or summing. Now, the interpretation of the variance is that it gives us a measure of how spread out or dispersed a distribution is. It's averaging, or it's measuring, it's giving us the average squared deviation about the mean. And so the greater the dispersion, the more spread out that the distribution is, then the greater the average squared deviation will be. The less dispersed a distribution is, then the smaller these deviations, these squared deviations are going to be, and so therefore the smaller the variance. So again, the variance is a measure of dispersion or spread that tells us how spread out the distribution is, or if we're thinking in terms of the random variable itself, how variable, how much variability that random variable exhibits. Now, note that the units of the variance are the square of the units of the random variable x. So, for example, if we're measuring income data, let's say income data measured in dollars, then the variance of that kind of a distribution would have units dollars squared, or square dollars. Now, I'm not quite sure how to interpret square dollars. There are other types of units which, when squared, perhaps are not very intuitive. And so for that reason, sometimes people don't like dealing with the variance. Now, one way to get a measure of variability that has units that are the same the data is to take the square root of the variance. All right, and so when you take the square root of the variance, you also have to take the square root of the units. And so then you would get back to units that are the same as the unit of measurement for the data. Now note that the variance can also be calculated using the following shortcut or computational formula. I'm also going to call this an expansion formula because we've got some additional formulas that we're going to obtain via expansion. And so the variance of x can also, which is defined to be the expected value of the square of the difference between x and its mean, can also be obtained in this way. The expected value of x squared minus the square of the expected value of x. Equivalently, the expected value of x squared minus the square of the mean of x. So we have the following ways of calculating the variance of the random variable, or the variance of its distribution. Via the definition formula, the expected value of the square of x minus its mean, or as the difference between the expected value of the square of x and the square of the expected value of x. Now, this computational formula is sometimes easier to use, and so that's why we have both. Now, it's not hard to prove. In fact, what I would encourage you to do is to see if you can prove that this shortcut formula is algebraically equivalent to the definition formula. So we were talking about the standard deviation a moment ago. Here's some notes on that. We have two ways that we'll be denoting the standard deviation. In letters, we might abbreviate it SD, so the standard deviation of x, using Greek letter notation. All right, we would denote it using lowercase sigma. Okay, and so we use sigma for that, the S sound, standard deviation. And in fact, this is why we denote the variance by sigma squared, because we use sigma for the standard deviation, and we know that the standard deviation is the square root of the variance. Therefore, the variance is the square of the standard deviation. And as I was saying before, one of the reasons we like to use the standard deviation is that the units of the standard deviation are the same as the units of the random variable x. Now, that's certainly not the only reason we like using the standard deviation, but it's one reason that it is perhaps more intuitive and more easily understood. Now, before we move on, let me just also say that we're talking about the units here. We're talking about units of the variance being the square of the units of the original data. We're talking about the units of the standard deviation being the units the same as the units of the original data, of the underlying data. We haven't really talked about the units of the mean, but the units of the mean are the same as the units of the underlying data. Now, another special expectation is an expectation that allows us to quantify the shape of a distribution. And the shape of a distribution is quantified using the skewness coefficient of the distribution of a random variable x. And the skewness coefficient is defined in the following way. In the numerator, it's a ratio to start off with, and the numerator of that fraction is the expected value of the third power of x minus its mean. Okay? So it's the expected value of x minus mu quantity cubed. The denominator is the variance of the distribution of x raised to the 3/2 power. Now, the units of the skewness coefficient, let's talk about this. The units of the numerator of this expression are the units of the original data, or the variable of measurement, raised to the 3rd power. In the denominator, remember that the units of the variance are the square of the units of the original data, and then we raise that to the 3/2 power. So overall, in the denominator, we have the units of the original data raised to the 3rd power. So the units are the same in the numerator and the denominator, and so they cancel out. And for that reason, the skewness coefficient is a unitless measure, right? It has no units. In addition, as I said before, it quantifies the shape of a distribution in a somewhat coarse way, but it still quantifies it. And so the way that we interpret the skewness coefficient is in the following way. If the skewness coefficient is 0, that indicates a symmetric distribution. If we take a graph of the PDF or PMF, depending upon whether we have a continuous or discrete random variable, and then graph that and draw a vertical line through the location of its mean, then if the distribution is symmetric, if it has a skewness coefficient of 0, then the left side will be a mirror image of the right side. On the other hand, if we have a negative skewness coefficient, then that indicates left skewness. Left skewness, if you'll remember from your previous statistics course, means that you've got a long skinny tail to the left. And then if you've got a positive value for the skewness coefficient, that indicates that you've got right skewness, and so you would have a long skinny tail to the right. Now, the greater the skewness coefficient is in magnitude, the greater the level of skewness in the distribution. Finally, we've got another characteristic that you may not be familiar with yet, but you will be in this course, the kurtosis of the distribution of x. This also is defined via a ratio. The numerator is the expected value of the fourth power of the difference between the random variable and its mean. So the expected value of x minus mu quantity raised to the fourth power. The denominator is the square of the variance. Now again, the units of the numerator are the units of the original data raised to the fourth power. The units in the denominator, likewise, are the units of the original data raised to the fourth power. And so the units cancel out, and so the kurtosis is a unitless quantity. Now, what does it measure? Well, if you think about what the numerator is doing, think about that difference. We're looking at differences, expected value of these differences between the values taken on by the random variable and its mean raised to the fourth power. So the farther x is from the mean, you can well imagine that raising that kind of a value to the fourth power is really making it large. Okay, and so the more likely it is that x takes on values that are far away from the mean, the greater this expected value in the numerator will be. And so the kurtosis is measuring the heaviness of the tails of the distribution. The heavier the tails, the more likely it is to have observations that are out far away from the mean, the greater the kurtosis will be. Likewise, the greater the kurtosis, the more likely it is to have values that are far away from the mean. And loosely, we describe that as a distribution having heavy tails. Now, why in the world would we be interested in something like this? Well, it's important for us to think about in applied statistics because many of the procedures that we use, in fact, most of them, and as you know, if you think back to the methods that you learned about in your first methods class, which is the prerequisite for this class, many of those procedures are based on an assumption that the underlying data come from a normal distribution. Now, a normal distribution has a particular level of kurtosis. If the population or distribution from which we're sampling has much heavier tails than a normal distribution, if it's got a greater amount of kurtosis, then the results that we obtain from a procedure that is based on an assumption of normality may not be appropriate or valid in that kind of a situation. Let me say that again. If we apply statistical methods that are based on an assumption of normality, and therefore a given level of kurtosis, if we apply those methods to data from populations or distributions that have a lot greater kurtosis, then we may get led astray. The results may not be valid. So it's a good idea to consider the kurtosis associated with a distribution that we're sampling from. And we would do that by looking at the kurtosis of the sample, the data that we obtain from that population. So continuing on, more generally, in terms of special expectations, the expected value of x to the kth power is called the kth raw moment. So for example, we saw the expected value of x. That's just the expected value of x raised to the first power. That we would call that the first raw moment. We saw the expected value of x squared in that computational formula for the variance. The expected value of x squared is the second raw moment. The expected value of x cubed will be the third raw moment. The expected value of x to the fourth power will be the fourth raw moment, and so forth. Next, the expected value of x minus mu raised to the kth power is called the kth central moment. And so the defining expectation for the variance, which would be the expected value of the square of x minus its mu, that is the second raw moment. We could have the numerator of the skewness coefficient is the third raw moment, and the numerator for the kurtosis is the fourth raw moment of x. And then finally, the expected value of x times x minus 1 times x minus 2 and so forth down to x minus k plus 1 for some value of k is called the kth factorial moment, which is useful primarily when working with discrete random variables.